to give us a talk on local codes. She received her PhD from MIT and is now an associate professor at Purdue. Hopefully everybody knows that already.
Thanks a lot. Okay, thanks, Henry. And thanks everyone for coming back from lunch. Um, so I'll be talking about locality and locality, especially in coding theory. And the goal of the talk is going to be especially to build up intuition into how people think about locality. Um, and talk about what has been done out there, which is a lot of work. So I won't be giving, I won't be able to talk about everything, but I'll talk about kind of like the main directions, mention about some recent breakthrough in locality and local locality of codes. And actually the past few years have been quite amazing in terms of breakthroughs. We have breakthroughs almost in everything we care about. And then I'll mention along the way some open problems. Okay, so feel free to interrupt me. Okay, so locality is a relatively modern notion in coding, and modern means kind of like from the 90s. And it refers to the setting where the algorithm doesn't get to see the entire data. In this case, doesn't get to see the entire code word or the entire received word, but it's allowed to interact with the data via what we call queries. So queries are essentially indices into the data. We ask a query, which means like what is the value of the data at position Q1, and we get back the value and position Q2 and so on and so forth. And the goal is to make as few queries as possible and still be able to solve interesting coding problems, even though we might encounter a lot of errors. So we have a very sublinear view of the data, yet we want to be able to solve interesting problems. Okay, so the important parameter of the talk will be, the most important parameter will be locality, which is the number of queries. And the goal is to perform as few queries as possible, so sublinear in the length of the input, ideally constantly many queries, but as we'll see, even queries that are sublinear anywhere in this range are going to be interesting regimes. So why do we care about locality? Well, this is in the context of large data, little time. Data is expensive to access, and because we really can do lots of interesting things with just a local view of the data. Okay, so the kind of things I'm going to talk about today are going to be locally testable codes, decodable and correctable codes, and some variants. And then locally recoverable or local reconstruction codes in the last part of the talk. Locally testable, decodable, and correctable codes have had a lot of applications throughout TCS. I'm listing here a few, but this is not a comprehensive list, and I'm not listing all the papers that are doing great work on these applications. I just wanted to emphasize that I will be talking about 3 error models: Hamming, which is the standard error model that we've seen in the past few days here. But I'll also be talking about insertion and deletions, insertion and deletion codes, and then erasures. So that's in the context of distributed storage. Okay. So let's start with locally testable codes. This is something that you've already kind of got a glimpse of in multiple talks this week. The general plan will be the following. I'm going to talk about what it means to for property. I'm going to talk about necessary conditions for testing, which constraints and characterizations are some. I'm going to talk about polynomial codes. I'm going to look at tests for polynomial codes a little bit more in detail, and some analysis vignettes, and then about how to come up with new codes from old ones, new LTCs from old ones via things like symmetry, lifting, tensoring. And this is all kind of to set up the stage for the big breakthrough on C3 LTCs that Prahlad is going to talk in detail tomorrow. Okay. So what is a locally testable code? A locally testable code is a code that for which there exists an algorithm that makes a few queries, let's say L queries, and is able to distinguish between the case when the received word is in the code or far from it, okay, with high probability. Okay, and these are the acceptance probability. These are standard notion of okay, completeness and soundness. If the queries can be seen in advance, then the tester is non-adaptive. Otherwise, it's called adaptive. Interestingly, for linear codes, it turns out that any two-sided non-adaptive test can be transformed into a one-sided, two-sided adaptive test can be transformed into a one-sided non-adaptive test. So non-adaptivity and two-sidedness, it's kind of irrelevant for linear codes. And there is a stronger version, which is the fact that the test not only rejects when it's far from the code, but it rejects with some probability that is proportional with the distance of the received word from the code. So this is a stronger version, and it turns out that all the codes that we're going to talk about today, including the C3 code, satisfy the stronger version. Okay. Okay, the upshot, the gold standard in locally testable codes has been for a long time achieving codes that have constant locality, constant rate and relative distance. There is a question?
Sorry, one-sided means perfect completeness? Or?
Perfect completeness, yeah. Exactly. So we always accept when we're seeing something from the code. And this is kind of important because it builds up into these notions that are coming up like constraints. Okay. So this has been the gold standard for a long time. It's now been resolved. Everybody talks about this new result by the era Livnal, Lebowski, and Moses. Let me start with kind of like the basics. So the first code that was proven to be locally testable was the Hadamard code. So the Hadamard code is just the set of vectors where each position A is the value at each position A is the inner product of A and X, where A and X are binary invariant vectors. And testing means given some received W output, yes, if W is a Hadamard code word, or reject if it is far from the Hadamard code. Okay, where far means Hamming distance. Okay, so here is the basic test. The basic test picks A and B uniformly at random, and it simply checks this very succinct property that W of A plus W of B equals W of A plus B. So it queries W at position A, B, and A plus B, and it just verifies that this condition holds over F2. Okay, so it's a very simple test. It's a very succinct test. It makes 3 queries. And why does it work? Well, completeness, it turns out to be trivial. Every linear code has this property, so we're always going to accept. Soundness is the hard part. And this is kind of like how pretty much every proof of testable codes works in like at a very high level. You go by proving the counterpositive, so assume that the test accepts with high probability, then W, we want to show that W is close to the code. Okay, so a very important step here that, again, turns out to be the crucial step in most of the proofs for testability of codes is this notion of self-correction, which is the following. So basically, we're given W, and we want to we want to find a code word that is close to W. Okay, so now we're going to explicitly define that code word as follows. At each position A, I'm going to look at the vote of B for A as W of A plus B minus W of B. Okay, so each B comes up with a vote for the value at this position. And depending on the field that we're working on, we're going to take the majority or the plurality over all these values. Okay, so we do this for every A. And what remains to be shown is that whatever we obtain, this CW is actually something that is close to W, right? We're close to the code, and that is a code word. Okay, that it is really a linear function in particular here. And this is the harder part in all of the proofs, showing that this apparently unstructured vector actually has a lot of structure. So this is the kind of like the magic of this BLR proof, is that it really kind of sets the stage for strategies for proving LTC-ness throughout the entire field. Okay, so the takeaway again is most proofs rely on defining on the self-correcting step where we take a vote for the value at each position, and then proving that the self-correction step gives us something that is close to the code and something that is something that is close to W and something that is in the code. Okay. So there's going to be a lot of hammers and nails. Thanks to Mary, she provided us with a lot of with these very nice pictures. But I think in my talk they're going to appear at random places, so don't don't take them too seriously. Okay, so local constraints. This is a necessary condition. What are these? So in the Hadamard case, we looked at A, B, and A plus B. These form a local constraint. Okay, so these form local constraints for linear codes. They are three local in the sense of we have only three things we're looking at, three positions. And sometimes people look at constraints, at the constraint set as a graph, a bipartite graph, where on the left-hand side we have the code word locations, and on the right-hand side we have vertices that represent constraints, and we have edges for between the constraint, the nodes in each constraint. Okay. So anyways, dual codes we all know. Let me, I just want to say something in two ways. So that's why I'm defining the dual code. So it's just the subspace dual to the code C for linear codes. And the observation I want to make here is that for every A and B, for every location, for every vector A and every two vectors A and B, the dual of the Hadamard code contains a code word that is supported on A, B, and A plus B, which means that I have ones in these locations and zero everywhere else. Okay, so this is a vector. You Can you imagine? It's a vector where I only have 3 ones at location A, B, and A plus B. Everywhere else, we have a 0. Okay, so what I'm saying here is that the dual contains kind of low-weight constraints. And just let me get there in a bit. So a canonical tester for linear codes is simply to pick a dual code word. And this is again a result of Ben-Sasson, Harsha, and Reskodnikova. And this implies that if we want L local testing, we need to have L local constraints. Constraints that are supported on at most L many locations. Okay, so dual contains code words of weight L, and the code has L local constraints. Okay, so this is a necessary condition for testing. What else is testable? Okay, we have linear codes. The next question people asked, what else is testable? And it turns out that pretty much everything we care and love is testable. So Reed-Solomon, Reed-Muller, dual BCH, affine invariant codes, lifted codes, multiplicity codes. We've seen quite a few of these definitions so far. So what I plan on doing next is to show a little bit more, to look a little bit more at the constraints or characterizations, or the tests that we have for each of these family of codes. Okay, so this is just to build more intuition of what people have done. And there is an enormous amount of work and in this area. People care about optimizing parameter soundness, the soundness parameter degrees versus field sizes, which is something that I'm not really going to go into, but I just want to kind of build up more intuition about what people, how people test things. And I'll tell you already the punchline, which is it's all about restricting to affine subspaces. Okay, so pretty much all the tests we're going to see are restrictions to affine subspaces, including lines. Lines is an affine subspace. And there is a hammer. Okay, so Reed-Solomon codes. These are evaluations of low-degree polynomials over a field F. Let's just call it F here of size n. So the goal can be reformulated as given F, is F a low-degree polynomial or it's far from it? Okay, that's what testing means. And the tests are built on something called local characterizations, which is characterizations that are constraints that kind of are satisfied with an if and only if in front of them. Okay, so basically that means here it means the following. We have the following local characterization. F is the degree D poly if and only if it satisfies this type of a constraint. So this is a linear combination of F when we evaluate F over a line. Okay, so I is from 0 to D plus 1. And we have some coefficients AI, which are they look like this. It doesn't matter. There exists some coefficients such that when you take these linear combinations of F restricted to this line, we get 0. Okay. So based on this local characterization, the test simply restricts F to point on this line and accepts if the constraint is satisfied, and otherwise it rejects.
Okay. Just for the AIs are different from the AI that pick at the beginning. It's not how to choose the.
Oh yeah, sorry. Yeah, they are different.
Okay.
They're different. Yeah, they should be called something else. Yeah, these are the evaluation points, and this is just a coefficient. Call it beta. Okay, so but it's a very nice property of low degree polynomials, and it follows from taking derivatives, essentially taking the ds plus 1 derivative. Okay, so what else how do we analyze this test? The self-correction step here is something like, well, look at all these evaluations and notice that when I equals 0, we just get f of x, right? And use the vote of the remaining points on the line to kind of like to vote for x, right? So pick a random line, vote for through x, vote for x using the values of the points on that line, and do this for every single line. Okay, so that's the value that we're going to set for p of x. That's the self-correction step, and we're going to take a plurality over all these values. And it turns out that because this is a characterization, I mean, there is lots of work going on in proving this. This is the hard step, as I mentioned before, but this characterization implies that this p of x that we obtain is actually a close-by code word, and it is a code word. Okay. So, okay. So just one. So this test, in terms of parameters, the locality is d plus 2. So we're looking at d plus 2 points here. Rate is something like d over n, and distance is n minus d. Okay, so if d is a constant, then rate is pretty bad. Let's look at the next step up. So read Muller codes. When we look at read Muller codes, the degree versus the size of the field or the characteristic of the field play a role. So maybe the first test for, let's talk about characteristic 2, is due to Alon, Kaufman, Krivilevich, Litzen, and Ron. And we have a similar local characterization here, which says the following. So pick an affine subspace through X. Okay. Look at the value of f at every single point on that affine subspace, sum it up, and you should get a 0. Okay, so if you sum up the value of f over the subspace of dimension d plus 1, you should get a 0. And as you can imagine, you can use this characterization to get a vote. Okay, here we're going to take majority because we're working over f2. And the upshot is a test with locality 2 to the L, 2 to the D, where D was the degree. But when D is a constant, then this is a constant degree, constant locality test. And this is also tight because of Reed-Muller, because of the distance of Reed-Muller codes. So we cannot have shorter constraints in the dual. Okay. Okay, so there's another hammer. What about larger characteristic fields? We have this general local characterization, which we've heard a couple of times. If we restrict f, so in general, we're looking at degree D polynomials in m variables over some field f. This time the field size is larger than the degree, and the local characterization that is used for testing is that f is a degree D polynomial if and only if restricted to affine subspaces through x is a degree at most D polynomial. And based on this sort of characterization, people have come up with many, many, many tests. This has been beaten up to death. This technique has been beaten up to death. Some of the tests that people study a lot is the restrict to a random line. Okay, find a low degree polynomial, find a univariate polynomial on the line, as we talked a couple of times about this test in previous lectures. Interpolate, pick a random point and check consistency. Okay, so this is called the line point test. It's been studied again and again, and I just noticed there is a recent paper by Prahlad and co-authors that kind of gets the best parameters for this test, a tight analysis for this test. So it's a very recent result. So another kind of a test is pick a two-dimensional affine subspace. And then pick a random point and check for consistency. This is called the plane point test. And another test is pick two-dimensional affine subspaces that intersect on a line, check consistency on the entire line, and accept only when we have agreement on the entire line. So this is kind of it's a test, or the high kind of like the conceptual contribution of this test due to Raz and Safra is that the tests themselves have quite a bit of agreement. Okay, so there is agreement between the tests, and somehow this local agreement will kind of propagate up into global agreement. So this is kind of like a crucial notion that eventually even plays a role in the, it's a powerful technique, and it plays a role conceptually, I'm just saying, in the C3 LTC result. Okay, so
There are all these tests. Like, is there any trade-off? Like, why?
There are trade-offs. There are many trade-offs between query complexity, soundness, D versus the degree versus the field size, robustness, which is actually something I'm going to define next. Yeah, there are many trade-offs. And yeah, you can define Reed-Muller codes over various fields and like prime fields or fields of the form P to the Q, and kind of like there are variants for many, many settings. So another notion of testing is that of robust testing. And again, this is a notion that that is satisfied by all the tests that people have cared about so far, or most of the tests, or the tests that we're talking about in this lecture. And this notion refers to the fact that if F is far from the code, when we take a local view, not only we realize that the local view is not what it should be, so we should just reject, but the local view is actually far from what it should be. Okay, so more kind of precisely, we want to reject kind of emphatically if F is far from the code. So if F is far from the code, then the projection onto whatever set we're projecting onto is far from kind of the code that should be C projected to S. So the expected distance between F and S and C restricted to S is at least some alpha, which is a constant times the distance from the code. Okay, so this is a stronger notion of testing. For instance, for Reed-Muller codes, so usually robust testing comes at the price of more queries. So one result about read-molar codes is that they are robustly testable for Q-square-many queries, and any alpha greater than 1 when the degree bound is almost as good as the field size. Anyways, I'm not going to dwell. I'm just, my goal here is to just tell you notions that people care about. I'm not, and the reason why this notion is going to be important is because of kind of recursive testing. When we want to test a big code by projecting into coordinates that should look like smaller codes, if the smaller code is a locally testable code and the code itself is robust with respect to these projections, then the big code is going to be locally testable with a little bit of a loss in soundness. But this is a robust testing is also a crucial notion of testing used in PCP and anywhere where we need to kind of recursively test.
Elena, when you have OQ squared, is that relative to M getting large while D stays fixed? What's growing?
So D is growing. So these kind of results were initially known for kind of small d, like Q over 2, about Q over 2. So I'm embarrassed, but I forgot to put a reference for this result. So this the big deal about this is that it works for even d that goes up to the field size, and I think alpha is actually a function of d. So yeah, d is growing and alpha is a function of d. Okay. Okay, so all the codes in this talks are robustly testable, but that's pretty much what I'm going to say about robust testing. So let me quickly summarize what we've learned so far, and then we're going to move on to other notions of other codes that are testable. So we've learned that local characterizations are affine subspaces, so they usually have a lot of structure. We care about structure when testing. Local constraints have or should have large pairwise agreement. That kind of leads, that kind of plays into the paradigm that local structure kind of creates global structure, or local agreement creates global agreement. And robust testing is useful in composing tests. And it turns out that all these ingredients are important in the C3 LTC result. Okay, so do we have any questions while I'm going to drink some water? Okay, so what else is testable? There is this kind of direction of research where people that was started with Kaufman and Sudan, where people wanted to characterize what exactly leads to testability. Okay, so do we have necessary and sufficient conditions for testability? So this is kind of a direction that is slightly disjoint, but also connected to that of finding best parameters for testability. But here we're asking what makes a property testable. Okay, so in particular, Kaufman and Sudan noticed that all the properties we looked at have this property that they're affine invariant. So, which means that, which means the following. So, a function, a code C is invariant under a permutation pi of the domain of F, if F in C implies that F composed to pi also belongs to the code. Okay, so In particular, a fine invariance means that f in C implies f of ax plus b also belongs to C for all affine maps that take x to ax plus b. Okay. So in particular, if we look at the Reed-Muller code on let's say m variables, any affine transformation of the variables is going to still land you into the code. The degree stays cannot increase. Okay, so one other observation we can make here is that, just also kind of in order to build some orientation, is that if C is a fine invariant and we have a constraint of variety K, let's say, then if you take every element of the constraint and permute it or permute it using the affine map, we're also going to end up with a constraint. So affine invariance plus one constraint, it will lead us to more constraints. Okay, so that's kind of nice. And there is an even stronger notion that which is called single orbit characterization, which says that essentially one constraint determines the code. In the sense of f belongs to C if and only if for all affine maps A, f composed to A also satisfies S. And I should have said that S is a local constraint for C. Okay, so if we have one local constraint S, the code is affine invariant, and if f is in the code if and only if f composed to A satisfies this constraint, then we have this property called L single orbit characterization. And this is a very nice property because it implies that the code is testable and locally testable. So this is a big theorem of Kaufman and Sudan, which essentially unifies the testability of everything that that we've known, we've seen so far, and even more. Okay, and I'm going to say a little bit more about even more. So because all these codes do have this property, single orbit characterization, so one can prove that all these codes are actually characterized by one single constraint. Okay. So one might ask, what do binary affine invariant codes look like? And I'll say a few words about about this. So in particular, if C is a code, let's talk about binary codes that apply F2 to the n, the field F2 to the n into F2, so the big field into the small field, is a affine invariant if and only if it can be described by a collection of degrees D, in the following sense, that C is exactly the set of polynomials of the form trace of P of x, where the degrees in P of x belong to this particular set, D. Okay, are people following, or have I lost? So there is so with each affine invariant code, you can associate a set of degrees, and those are the only degrees that you can see inside the trace function. Okay, so I think I know why people might have been lost, because the trace function is this function here. It maps F2 to the n into F2, right? So it maps the big field into the small field. And it really just looks like this. It has very nice properties, like it's a linear function, trace of x plus trace of y equals trace of x plus y. Raising the trace of something to the power 2 to the I. Yes?
Just to clarify, we say like the code words are a trace of px. Wouldn't those be like the messages? And then I guess the code words would be the evaluations.
So the code words are, I'm thinking of evaluations of traces.
Yeah. Evaluations of traces.
Yeah.
At all points in F2 to the end.
Yeah. Okay.
And now P is a polynomial with coefficients in F 2D.
with coefficients in f2 to the n. Here we can play whatever we want. We're going to end up in f2 to the n, but we're going to be mapped down to f2 by the trace function.
And then is set D an arbitrary set, or is it like up to some number?
It's a set of degrees up to 2 to the n minus 1.
Is it contiguous, or is it like some sparse set?
So it with each affine invariant property, you can associate a set D, but you do need some properties. It's not. So actually, I'm going to say next. Reed Muller of order 2, for instance, can be viewed as a univariate polynomial where the set of degrees have binary weight 2. So they only look like 2 to the I plus 2 to the j. Reed Muller of order W is all sets of degrees that have binary weight W. Okay, dual BCH D is bounded. I'm lying a little bit here, but essentially the set of degree there are some equivalence classes, and the set of degrees that we care about is bounded. Then sparse codes are affine invariant codes for which the set of degrees is small. So it's a generalization of dual BCH. They don't have to be up to T, but there is a small size set that describes the degrees. Okay, so this I have some conjectures here. This is something I worked on during my PhD and broke my heart. So I'll just quickly mention them. So we want necessary and condition for a family of codes to be affine invariant. And the conjecture is that binary affine invariant code, when n is prime, is testable if and only if it's either Reed Muller or a sparse code. Okay, so it's a very simple to state conjecture. We know that these are testable, so we know one direction. And in general, affine invariant codes are testable if and only if they can be obtained from Reed Muller and sparse codes via some operations, addition, intersection, or lifting, which is something I'm going to talk about next. Okay. So how do we obtain new codes from old ones, new codes from lifting? We have a base code. We've already seen this, so I'm going to quickly go over this definition. We have a base code B, and the lift of B is the set of all functions, and I can add as many variables as I want, such that the restriction of F to every single line belongs to the code B. Yes?
Just to clarify, on the previous slide, you were talking only about binary codes, but is there a similar statement?
Oh, so this is for the non-binary. This is the general statement.
Okay, but the statement about it's not
that's-
binary, definitely if it's the trace, it can be viewed as this trace. Could I have a similar statement just over, say, like prime fields or? Like,
Yeah, I mean, even in general, you can. Okay, so how do you get the degrees? You have to be more careful. But yeah, so one property of the degrees is that they are closed under kind of removing 2 to the I powers. So there are some properties of the set of degrees that you can use. So I need to remember what happens for general fields. But yeah, once you take plus is easy. Lifts is what can mess up things, and I'm not sure if one can characterize precisely how the degrees look like. But yeah, we can talk offline. Yeah. Okay. So restrictions to every line keeps you in the code, and more generally, restrictions to any t-dimensional subspace keeps you in the code. Okay, wow, I think I'm, yes.
I had a question about the conjecture in the previous slide.
Oh.
Regarding the first conjecture, is it true if, say, like 2 to the n minus 1 is prime?
I don't think we know some things, but no, I don't think it's no. Or to the n minus 1 being the prime. Yeah, we know some things, but and actually it can be described. I can talk offline about this, but yeah. Anyways, let's move on because I realize that I've been really slow. Okay, so lifting, you can also define lifting by using restrictions to two-dimensional subspaces. Lifting gives new families of codes, in particular lifts of Reed-Muller, and gives you possibly not Reed-Muller things. And the upshot is that Guo, Koparty, and Sudan created new families of testable codes with locality that is in this regime and to the epsilon and high rate, constant distance, using lifts, which was the first time such a result was obtained. And then similar ranges of parameters have been obtained even afterwards, where so tensoring, which is something that Mary talked about last time, and I'm actually going to go very quickly over this. Restrictions to lines don't work, but kind of the nicest test here is projections to two-dimensional spaces. So if you want to test tensors of M, versions of B, projections to two-dimensional spaces works out. Multiplicity codes, this is exactly what Prahlad talked about earlier, so I'm going to skip. So in terms of state of the art before C3, we have constant locality LTCs with rate 1/polylog. These are the PCP type constructions. And then the results we saw before. And actually the last one here is by Koparty, Meyer, Ron, and Zevi and Saraf. It's kind of a very intriguing result because people didn't expect to get to locality n to the low of 1. Actually, all these tests have lower bounds of n to the epsilon. So this was a huge surprise, and these are codes that that were obtained via the Alon-Luby transform, which again Mary talked about last time. So, anyways, after so this is kind of like the classical work on locally testable codes. In the past 10 years, there has been a lot of work of local testability from the perspective of high-dimensional expanders. These are kind of high-dimensional versions of LDPC codes or tenor codes. It turns out that LDPC codes are actually not testable, but somehow some versions of LDPC eventually can be built into a testable codes. But the interesting thing I wanted to say here is that all the tests that I've been telling you about, these projections to affine subspaces, can be explained from the perspective of high-dimensional random walks in high-dimensional Grassmannian complexes, which are kind of like multipartite graphs where each part contains, let's say, on one side points, on another side planes, on another side cubes, and the edges represent the inclusion. So the test that we've looked at, there is an explicit link between something called agreement expanders and all these testing results that we've seen. Okay, so Anyways, this is just putting everything together in one slide. The C3 LTC code, this is a kind of a teaser for the talk of Prahlad tomorrow. And actually we've seen Nick's talk earlier today. The code is a lift of a product code for some very special a C prime and C double prime. The test is pick a random constraint and test if we see a code word in C prime times C double prime. And the keywords here, robustness, constraints, have many agreements, expanded graphs, cell correction are all kind of keywords into the proof that we're going to see tomorrow and see the proof tomorrow. Okay, so I think I took way too much time for this part of the talk. Let's move on into locally decodable codes and relatives. So I want to talk about some state-of-the-art results, some proof strategies for the lower bound. Wanted to build up a little bit into the breakthrough results, the new lower bounds that came up last year, and some relatives. And then in the next lecture, I'll talk about insertion deletion, locally decodable codes. Okay, so locally decodable codes, these are codes for which we want to decode each bit of the message very quickly. So we want to make a few queries into the received word and be able to decode for each bit of the message the value xi by just making a few queries. Okay, so we want to decode the probability at least half plus epsilon. And I'm going to not stare at the definition too much longer. But again, a standard example of a two-query locally decodable code is the Hadamard code. The previous property that we saw, again, gives us a two-query locally decodable code. There is a related notion, locally correctable codes. These are codes for which I'm even removing the message. We want to be able to quickly recover each bit of the encoding itself, the code word. So the code word bit I, we want to recover it with probability at least half plus epsilon. And again, the Hadamard code, as you would expect, is a two-query locally correctable code. And just a quick observation here, linear locally correctable codes are actually locally decodable codes because they are systematic. So the message bits are appear in the code word. Okay. So locally decodable codes from from Reed-Muller codes. Guess what? The same restriction to lines gives us a local decoder for Reed-Muller codes. And if you play with the parameters, this is the kind of trade-offs you get. You get, for locality constant, we get exponential length LDCs. For locality that looks like polylog n, we get almost linear codes. And locality that is about n to the epsilon, we get constant rate codes where the rate depends on epsilon. And the state of the art in the other regimes is, so we have a lower bound for two queries. What we saw, the Hadamard code is the best you can do for two queries. For three queries, there was a breakthrough result of Yekanin and with follow-up works by many others that gave a sub-exponential length locally decodable codes for three queries. And here the lower bound till very recently was just n squared. Okay, and the remaining regime is exactly what happened, the same kind of trade-offs that we have for locally testable codes for some reason. So let me quickly say a few words about lower bounds. So the kind of upshot here, what everybody studies is a particular So one can show that for each message bit I, we can associate a hypergraph, where the vertices of the hypergraph are the elements of the code word. And each hyper edge contains a Q query. Okay, so the queries that the local decoder should make, you can create a hyper edge out of, let's say, a particular Q query that the decoder makes. And this hypergraph, this Q uniform hypergraph turns out to have a large matching in the sense of a large number of edges that do not intersect. So the queries, the tuples of queries do not intersect. So in particular, there exists a large matching of size, let's say when Q is a constant, linear. Okay, so for each I, we have such a hypergraph with a large matching, and the remaining proofs for lower bounds essentially analyze this matching. Just a few words about this new breakthrough result of Arabian, Guruswamy, Kotari, and Manohar from last year. So for the first time, they break the K-squared barrier and obtain a K cube, omega K cube lower bound. So this is an amazing result. It's been more than, I don't know, 15 years that we've seen an improvement on the lower bound. And just a few words about the proof. So the proof makes kind of views the so first of all, the queries that the decoder makes, you can write down a system of equations with one equation per tuple of queries. So for instance, here I'm color coding the hypergraph, let's say for message bit 1. And we're looking at 3 queries. So x1, x4, x6 form a query, x2, x3, x10 form a query, 5, 7, 9 form a query. And we can write this linear system of equations for that is supposed to have a solution that satisfies at least half plus epsilon of these equations. So one can view this system as a constraint satisfaction problem. And here the strategy is to show a lower bound is to find what's called the refutation algorithm to the system having a large value, half plus epsilon. Of course, they do a lot of work, and they build on results on semi-random CSP refutations that some very recent results and some breakthrough from a few years ago. So, anyways, this is just kind of like the starting point of their proof. And then a subset of the authors get kind of like your dream lower bound, an exponential lower bound for not LDCs, but for LCCs, linear LCCs. So 3-query linear LCCs must have exponential length. So this is, again, a fantastic result. It's all you can expect. So essentially, this gives us, it solves the problem for 3-query LCCs. It matches the Reed-Muller linear LCCs. It matches the Reed-Muller upper bound up to poly K factors. And it also shows a strong separation between locally correctable and locally decodable codes, which is something we didn't know. So the constructions of Yekanin are not locally correctable. And of course, I mean, there are open problems to extend. That's going to be really hard open problems, but we want to extend to any locally decodable code or improve the upper bound and also extend to nonlinear SC. I think I'm out of time, or do I have 5 minutes or
So, yeah, so I think 5 minutes is fine.
5 minutes? Okay. So just very quickly, there is a variant called relaxed locally decodable code. And in this variant, the decoder is allowed to say, I don't know. It's allowed to fail. So it's allowed to fail, but it's not allowed to fail by too much. So for each message bit, it should respond with the correct bit, or I don't know, with probability half plus epsilon. And it should actually respond with the correct bit for a large fraction of message bits. Okay, so it turns out that these three properties are actually, the third property is not is implied by 1 and 2, but it will be maybe more relevant when I'll talk about insertion deletion codes. But the big theorem here is due to Ben-Sasson, Goldreich, Harsha, Sudan, and Badan, improved by Asadi and Shinkar recently, which says that if you allow to output bot, the rate decreases kind of dramatically. So we can construct constant query relaxed LDCs with essentially linear size, linear length, and this matches the lower bounds that were proved recently. Okay, so there was a question that was asked by Gore and Lachish, which is what happens for Q equals 2. So there exists a Q, but we don't know, it's a large Q. What about Q equals 2? Are there linear or almost linear RLCs? And this is a question that we managed to solve recently, and we essentially prove an exponential lower bound for 2 queries. So these are RLDCs with exponential lower bounds. And I'm listing 2 problems here that I think are kind of doable. They're nothing like in the space of problems that we see, the breakthrough type questions. This lower bounds holds when with the definition that perfect completeness holds for the RLDC. So we want to output always the correct bit if we don't have errors. And there is this corollary here that for some constant query complexity, the length drops from super polynomial to polynomial just from Q to Q plus 1. And we thought it would be interesting to see where this drop happens. Okay, so I think I'll stop here. Yeah, thanks for your attention.
All right, I think we have time for a couple of questions. I have a question about the last point. So is it clear it has to drop on Q plus 1?
Yeah.
Over a range?
Yeah, so we have the exponential lower bound at 2, and somewhere it's n to the 1 plus.
So there exists some Q naught for which.
So there exists some Q where it drops right. It's a sharp transition, essentially.
All right, let's think. Elena, one more time.